Welcome to Computer Science 305. Today we're going to be talking about memory management. And so, in any programming system, we have to have some sort of dynamic memory allocation, right? We started talking about this in when we were talking about memory locations for variables, but now we actually have to talk about how that's actually done, right? We talked about creating of allocations for activation records, things like that. Now I actually understand how this works. And so, lots of things need memory at runtime, specifically, as I just mentioned, activation records. In object-oriented systems, we actually have to create objects, right? So those have to be out there. And then any other type of explicit allocations, right, when we actually use the keyword, for example, new in Java or malloc in C and C++. And then finally, like any implicit allocations, right? Strings, file buffer sizes, arrays with dynamically varying size, etc. All these different things have to be actually allocated somehow by the language system, right? So, in order to do this, these systems have an underlying component called the runtime memory management. And so we'll be talking about that, and so we're going to specifically looking at this in the context of the Java programming system. And how we're going to do this is we'll first talk about the concept of how we model memory using Java arrays as our basis for understanding this. And we'll start talking about the stack versus the heap, and then heap links, and then finally we'll get to garbage collection, which we've been alluding to since back when we were talking about, like the last 3 or 4 lectures. So, the memory model. For right now, we're going to assume that the operating system is going to grant us some sort of, each running program their own fixed size region of memory for dynamic allocation, right? And if we assume that, then we can use the Java array as essentially a construct to represent how memory is actually, managed. And we'll see this in practice with Java. So basically, let's think about this, right? We declare an array in Java, right? It's an integer. We make an integer array, and we initialize it to null, right? It's empty. It points to nothing. And what we want to do is we want to take the, we have to understand first, of course, that an array is a type of object, right? And then the variable that we're pointing to is actually the variable that we have is actually a reference to that array in memory. And so we initialize our variable a to null, but we know that it can hold an array of int values, but currently has nothing in it. So when we go to create the array, we have to use the new keyword, right? And the new keyword, obviously, as we mentioned at the beginning of this lecture, is a method by which we allocate memory. And so when we do this and we allocate an array of size 100, what's really doing is that's going to be constructing an array, an amount of memory equivalent to 100 times the size of each an individual integer in Java, which happens to be 32 bits. So now that we have that, we can think about this in a different way, right? Well, we could also have done what we just showed up above as a single line where it was int square bracket a equals new int 100, right? And that's fine. So we want to use this array, right? For example, in a while loop, we go from I is less than, we have some integer counter, right, equal to 0, starting at the 0th index of the array, and walking to the length of the array minus 1. So from 0 to 99 in the case of a. And then what we're going to do is we're going to initialize each of these individual parts of the array to the value of 5, and then we're going to increment our counter by 1. So when we do this, right, when we're actually saying a in square bracket I, what we're doing is, we got to go back to the concept of the L value, R value thing. In this case, the a square bracket I is the R value, right? Or sorry, the L value of the concept, right? and the expression the 5 expression is the R value, right? But the overall expression is just an expression statement. So we have we can use a.length, the axis length of the array. Array indexes are 0 to length minus 1, as we already said. So we know what's kind of going on here. We just have to kind of understand how this is actually helping us. So if we were to have a memory manager, and I'm not going to implement this straight up, but basically what we have here is we're just going to create this memory manager, and it has an integer that is representing integer array representing our memory, and we have a constructor that constructs our memory manager with an initial amount of memory, right? And then we can use that to construct and deconstruct and or allocate, deallocate actual memory from that memory region. So this gets us into the concept of a stack. Okay, so remember we talked about activation records in languages like Java as being a stack of activation records, where we're keeping track of things like the most recent or the current executing activation record, as well as we have pointers to different things, so we can do different things like recursion, and then we push on call and pop on the return of the method. All these things are happening, but it's basically a simple management problem. So basically, if we have our stack, right, the top of the stack is index 8, and the bottom of the stack is, of course, index 0. So if we have an empty stack of 8 words, words is a typical definition for the size of memory in a memory register, if we recall from our course on architecture. The stack will grow down from high addresses to lower addresses, and a reserved memory location, perhaps a register, records the address of the lowest allocated word. So we think about this, right? We have, if we want to create an activation record, right, the program calls we have from 7 through 5 is our first activation record, and then we have the top, which is the register, which is now pointing to 4, right? So the program calls m.push3, which returns 5, the address of the first of the 3 words allocated for an activation record. Memory management uses an extra word to record the previous value of top, right? So we're going to say that the previous value of top, which was 8, if we recall, right here, and now we're storing that in the 4, which tells us what the new top is. So continuing along, right, we have a second activation record. The program calls m.push2, which returns 2, the address of the first of the 2 words allocated for an activation record, right? And then the stack is now full. There's no room for even m.push1, right? Because we need at least 2 things for that. And the interesting thing is we had to, again, record the top, and we had to record the previous top in the next location, which is what 1 is saying 4. So then we say for m.pop, right, we just do top equals memory top, and then return to the previous configuration. So when we call pop, right, we say top is equal to memory at top, right? So the memory at the top value, right, which is 4, is now the current top, right? So that is deallocating anything, essentially causing a deallocation. So if we were to do this as a stack of implementation, right, we again see what we have. We have a stack manager, which has a integer array of memory, and then we have our current index of top, like a current value of top. And then we have the stack manager constructor, which is going to take in the the initial memory block, the array of memory, and then we're going to set our top to be the length of the memory, right? So beyond the last index. So we go do that, and we have to have our allocator, right? So if we want to allocate a block and return its address, we need to know, 1, how many blocks do we need, right? So and then what the return, and then we're going to return the address of that block, and then we're going to throw a Stack Overflow error if we're out of stack space. So we go ahead and if we go and call push, we say our old top is equal to our current top, Then we say top minus equals the request size plus 1, right? Because we have to have that extra one where we're going to record the top, the previous top. And then we're going to say if top is less than 0, after that, we're going to throw a stack overflow error because we overflowed the stack because we ran out of memory. And then we're going to say if that's not the case, then we'll say memory at top equals old top, the value that we cared about, and then we're going to return top plus 1, which is the location where we're at. So now we go ahead, and that's the start address for that activation record. So then the throw statement, right, is a part of exception handling, which we'll cover in a later chapter. I'm not going to get deep into it right here. Finally, when we go to pop the stack, right, basically it's just what we just talked about. We're going to say top is equal to the value at memory top. Makes sense, right? We just talked about why that works. So that'd be the basic concept of how we would handle a stack of activation records. Now, that works really great when all we have is functions that are being, or methods being called. But not when we have objects. Objects are a little bit more difficult to handle. And so that's why we have the heap. So the heap problem, right? So stacks make it easy. Stack order makes implementation pretty easy, but it's not always possible. Like the problem is what if allocations, deallocations can come in any order, which is, for example, with objects. And so what we instead want to do is we just have this pool of memory from which we can, which is unordered. We don't care. It's just an area that gives us a place to put things that we need to have in memory. And there's lots of different mechanisms to handle this. There's the concept of the first fit, right? So it's a linked list implementation. So we have a linked list of free blocks, initially containing one large free block. And so when we allocate, what we're going to do is we're going to search for the first adequately sized block. If there is extra space in the block, we return the unused portion at the upper end of the free list, right? So we're going to cordon off the size that we need, and then we'll return a reduced size of free memory. So that is the remainder of that block, right? And then if we want to free, we just add to the front of the free list, right? So if we essentially every time we allocate memory, what we're doing is we're allocating a new part. We're breaking the list down into pieces, and so anything that's free is just add to the end of the free or the front of that free list, right? Growing the list as we need to, or shrinking it as we need to. So essentially, we have a used area and an unused area, and they grow and shrink as things are created. So if we want to think about it, right? So if we want to use this as a list, we have a heap manager M with a memory array of 10 words, initially empty. And so we have this linked list, right? And so the head of the list down here at the bottom is held in the free start, right? So wherever free memory starts is held in the variable free start. And every block, allocate or free, has its length in its first word. So in this case, the first word is -1 because there's nothing available, right? There's no blocks allocated. So we get to this concept where we want to allocate 4 blocks, right? So P1 will be 1, the address of the first of the 4 allocated words, as we can see here, and then we have an extra word that holds the block length, which is 5, right? That would be 0. 0 holds 5, right? And then we have the remainder of the free block was returned to the free list. So that would be this thing, right? I think that's correct. Yeah. And so free start then points to 5, right? Because that is obviously the head of the free list. So we're good to go. Now we allocate another one. So we say P2 equals m.allocate2, right? Where 6 is the address, right, of the start of the new allocated block. An extra word holds the block length, 3, right? And then the remainder of the free block was returned as a free list, which is 8, right? So that's this thing, and then it's 2 in size. Excellent. All right. So then we continue along. And now we have to deallocate, right? So if we deallocate the first allocated block, it returns the head of the free list. So now we go deallocate, and so it returns the head of the free list, which is 8, right? And so now we have a pointer. So essentially we see here we have the free start is now 0. We have to effectively clear that out, but then we have, that's the size of this piece, right? 1, 2, 3, 4, 5. It allocates, and then it has the next pointer points to the next part of the free block. So then it goes 2 in size, and then now we have effectively 7 blocks of free space, which makes sense. Now if we need to allocate size of 1, right, we start back here at the beginning, and we essentially say P1, P3 is going to be 1, right, which is the address here, starting of the allocated block. We need the extra piece here to tell us the size of what's going on. And then our new one, which is the free start, now points to 2, right, which tells us that we have 3 blocks free here. The first element after that tells us that we have 8 in total. Points to 8, which is the next part of the free list, which then has 2 available. So we can use that, right? Now there were 2 suitable blocks, right? And that's the interesting thing here. If we go back, when it initially was doing this, there was two free blocks that would have been suitable to the size of 1 that we needed. One that was very large, and one that was the exact size, right? And so this just was first available versus best fit, and best fit is another possible mechanism. If we were doing that, we would have found the one that has the same size that we needed, which would have been this latter one, the end of the list rather than the beginning. So if we were to implement this in Java, right, just to understand it, we create a class called Heap Manager, which now has a static, a private static file int called null, right? This is the null link, representing that there's nothing in memory. And so that's -1. And so we then have our memory block, right? The memory that we're going to manage. And then we have a private int that's called free start. It's the start of the free list. And so then we go ahead, we initialize with a constructor our heap manager, and we do 4 things. First, we're given the initial memory, right, the block that we're going to manage. And then we set memory 0 equal to the memory.length, right, because it's just initially one empty block of memory. And then we have memory 1, which is equal to null, right, which is what the free list ends with. And then finally we have free start equal to 0. Right, because that's the start index of the block. So then we go ahead and allocate a block. If we want to do that, we have to have the size. That's all we need. Once we have the size, we then we say that we actually have to check it that the size is equal to the requested size plus 1, because it needs the extra place for indicating the starting location. And then we do a first fit search, right? So linear search the free list, looking for the first free block of sufficient size. So that's pretty simple. We just kind of walk through, looking at the next item after the first block tells us the size, and we say, okay, that's how big it is. If we find one, if we can't find any block that's large enough to hold the requested the actual size, then we throw an out of memory error. All right. Now, if we could, what we're going to do is we're going to basically have to adjust this so that we know what's going on in our list, right? So we have we say unused is equal to the memory at p minus the size, right? If unused is greater than 1, right? If more than a header's worth, the next free is p plus the size, right? And then the memory at next free is equal to unused, etc. Blah, blah, blah. But basically, we're just kind of walking down, and this is just the implementation of what we've already talked about, right? And then finally, we link out the block we are allocating, and done, right? So we, if the leg is equal to null, free star is equal to next free. If the memory at leg plus 1 is equal to next free, then we return p plus 1. Index of the usable word after the header. So finally, the deallocation works is pretty simple, right? Much more simple than the allocation, right? All we have to do is say we are given the address of the block that we want to deallocate. So we have to first start at the address -1, right? Because that's where the actual start of the block is. And we say memory at address +1 equals free start equals address, and then it essentially deallocates it for us. All right. So there's a problem, right? If we can actually create a sequence which will set it up so that we'll have enough free space in the memory total to allocate to do the allocation. But unfortunately, because of the way the blocks are broken up, we never would have enough. We never have a way to actually reverse the process correctly. So what this is telling us is that if we're going to do this type of thing, what we end up having to do is we need, instead of having it just where we consistently keep breaking the list up into these separate disjoint parts, we actually need to start coalescing adjacent free blocks into full free blocks. And we do that by actually creating a smarter deallocate method. So when we basically what we're going to do is we want to maintain the free list sorted in address order. And then when we free things up, we look at the previous free block and and the next free block. If adjacent, we coalesce them together, right? And that ends up becoming this method here, right? So we have our initial address, right, that we're given, and the address of the real star of the block will be the address -1. And then we're going to go and we say, all right, well, we have P is going to be our free start, right? So we have to find the insertion point in the sorted free list for this block that we're going to free up, right? And then what we're going to do is we say leg is equal to null while P is not equal to null and the P is less than the address. Leg equals P, and then P equals the memory of P plus 1, right? So essentially we're just going to be walking along and joining everything together in one large list. Now P is the index of the block to come after ours if in the free list, or null. And leg is the index of the block to come before ours in the free list, or null. So if the one that come after ours is adjacent to it, merge it with ours and restore the property described above. So basically what we're doing is we're just going to, this is telling us that if we find two things that are next to each other, we're just going to jam them together. I'm not going to go through all this. Anyway. So quick lists, right? So small blocks tend to be allocated and deallocated much more frequently, right? And so common optimization is to keep separate free lists for popular small block sizes. So these are just really easy to access and well-known things. So on these quick lists, blocks are one specific size. They have delayed coalescing, right? Free blocks are on quick lists, not coalesce right away, but may have to be coalesced eventually, right? There are times when we actually have to allocate a large amount of memory, so we have to coalesce them eventually. Fragmentation, that's when your free regions are separated by allocated blocks, and so that's not possible to allocate all of the free memory as one block. More generally, anytime heap manager is unable to allocate free memory, allocate memory even though free, right? So this is the problem. Essentially, you have a bunch of disjointed free blocks, right? Before, what we were doing is we were saying, well, there's a problem when you have all these allocation and deallocations. You could have it so that you have a bunch of adjacent free blocks that are not coalesced as a single one, so it doesn't know that it has enough room to fill that in. So we jam them together and to make them one large one again. But here we have the problem of we have a whole bunch of free blocks. We maybe have enough memory to allocate, but they're not adjacent to each other, so we can't actually do the allocation. So that's the problem, right? And that's what we just talked about. If we allocate 4, right, initially, and then allocate 1, and we deallocate P1, right, which was the 4, which is, it would allocate this whole section, then allocate this section, and then deallocate this section here. And then we try to allocate 5. We have enough memory because we have 8 blocks of memory and we need 6. But unfortunately, we don't have any one block that's large enough. And that's the problem. So we need to find a way to deal with that. Now, on the other hand, there are lots of other ways of doing this, right? Lots of different approaches, but there are three major issues. One is, where do you allocate the block? When and how can you split up large blocks? And then when and how do you recombine large free blocks? And so there's lots of other refinements and things. The ultimate goal of this is always to, one, make so it's efficient in the allocation, deallocation, while also ensuring that you are optimizing the use of memory as best as possible. So when we talk about placement, right, and we're looking at where to allocate a block, typically our in the first fit approach was FIFO free list, right? Some mechanisms use this similar linked list of free blocks, first fit, best fit, next fit, etc. Some mechanisms use more scalable data structure like a balanced binary tree. There's lots of different approaches, as we've already said. When we want to look at splitting, this is how to split up large blocks, right? So when we did the splits in our approach, we were looking at splitting on requested size +1, right? Sometimes you can get better results with less splitting. You just end up, so you have, essentially, you could have where you have block sizes specific, like you have some multiple that is, you would end up having like, here's my minimum size, like maybe the minimum size is 2. And so if someone requests a 3, well, you only give them a multiple of 2, so you would give them a 4, right? If they requested, a 6, they would get an 8, or maybe they get 2, right? Depending on what you're doing. I would say probably typical is 4 blocks, 8 blocks, 16 blocks, something like that. But that just gives it a little bit easier for you to make the management happen, and it's more it's a trade-off between efficiency of allocation versus efficiency of memory use. So then finally, coalescing, like how do we recombine adjacent free blocks? We saw several varieties. You just don't do it at all. You can do eager coalescing versus delayed coalescing, which is with our quick links that we talked about. Finally, now we'll talk about heap links, right? So now this is the interesting part. So we've been talking about, basically, you could consider like a running program like some magic black box of allocations and deallocations. But the question becomes, what does the running program do with the addresses allocated to it, right? So we actually have these things, right? So some systems track the current heap links. So a current heap link is just a memory location where a value is stored that the running program will use as a heap address, right? So it just gives us a way to link back to the heap and anything that's in there. So for example, think of like a variable in Java that references an object. So we can trace the heap link, right? So you have the stack. So the stack has the activation record for main. We have A, B, and C. So A points to some object in the state, in the heap, right? Which in this case is this item head 1, which then points to its tail, to 2, which has tail null, right? But A points to this one here, right? Start. So if we can take a look at this, right? That's our basic program. Int A equals new int list, null, int B equals 2, int C equals 1, and we've kept renaming A. We kept reassigning A to be the consing of B and C. So that's how we get the cons list here in the heap. So the question is, where are the current heap links in this picture? Well, in order to find those, right, we start with the root set, right, memory locations outside the heap with links into the heap. These are typically activation record, the active activation record for a function or a method, which is normally on the stack, not on the heap. But if it's a class method, it's on the heap, right? We have to understand that. Static variables defined outside of the heap, not as a part of a class, but we'll talk about this later. But for each memory location in the set, look at the allocated block it points to and add all the memory locations in that block, right? So repeat until new locations are found. So what this will do is that tells us what references. Basically, we're asking ourselves, where are the references to these things, right? So if we go back to the heap, right, we can see that in the stack, A references this item in the heap, which then references this item in the heap, which references that item. That's good. All right. So we see all the references, right? But essentially, if we never get rid of one of the, if we never have any references outside the heap, the question becomes, do we actually need this thing at all? Anyway, so the question becomes, we want to discard impossible links, right? So depending on the language implementation, we may be able to discard some locations from the set. So we don't have to worry about any locations that don't actually point to any allocated heap blocks. And if they don't point to allocate heap blocks, which is a thing from Java, right? So if the dynamic type rules out use as heap links, so that means basically, if they have dynamic type rules, if their dynamic type rules out the use of heap links, which could be dynamic type, could be, we're thinking of things like whatever it's evaluated to as part of the expression, or if they are coalescible types like inheritance. So if their static type rules, them out as heap links, which is, for example, in Java, if they have a primitive type, primitives can never be allocated on the heap. They have to be allocated on the stack. So we know that if it's pointing to that, then it's never going to be a link to anything in the heap. So now, then we have to ask ourselves, if there's errors in heap links, right? So we have exclusion errors, which is basically just which is an actual link to a memory location on the heap, but it's been left out for some reason. And then furthermore, we have unused inclusion errors, right? So a memory location is included, but the program never actually uses that value. So that could be something that's, for example, defined inside of a block, like in an if that's never, for example, you have if true, and then you define a variable that would link to the heap, but it's in the else clause, but that'll never be executed. That could be something that's never possible, that we should not worry about. Use inclusion errors, so this would be like a pointer error, right? So you have a memory location is included, but the program uses the value stored there as something other than a heap address, so as an integer, right? Which is something we can normally do in, for example, C, but it's not something we should ever use in Java. So you can't ever get around these. Some of these errors will occur regardless of your technique or the approach that you use. But how we actually recover from those is what makes it important. Right. So oftentimes, like for heap management purposes, exclusion errors exclusion errors themselves are unacceptable. We should never exclude something that shouldn't be excluded. And then we must include a location if it might be used as a heap link, which causes an inclusion error. Right. This makes unused inclusion errors unavoidable. So that's obvious, but depending on the actual language, using used inclusions may also be unavoidable, right? So if we accidentally give them the capability to use inclusions that in the wrong way, we may not be able to escape that. For example, in C uses pointers as you can use do pointer arithmetic. That's sort of like an inclusion error, but not necessarily as something that we should be worried too much about in Java. As I just said, use inclusion errors in C, right? Static type and runtime value may be the static type and runtime value may be of no use in telling us how a value will be used, right? So if our variable x may be used either as a pointer or as an array of 4 characters, right? Then we actually don't know if they're going to try to add, if they're going to try to do math to this. For example, if I define an array with malloc, I can actually, that will return a pointer to the start of that array, and then I can use pointer arithmetic to walk each value of that array. Well, that's all good and everything, and this union is going to allow me to do the same thing, right? I can either work with the pointer, or I can manipulate. If I do the same type of addition, though, it will actually instead add to that character, right, itself at whatever the initial value is. So that things like this can cause all sorts of weird errors that we don't want them to deal with. Now, all that aside, right, when we want to utilize, we can utilize heap links as a way to help us compact down the actual heap itself, and to manipulate the heap so that we can make coalesced free memory together while also moving already allocated blocks, right? So if we know all the heap links, then we can easily go ahead and move them around while updating any links to that block. So we can, that gives us the capability to avoid fragmentation and maintain one large free block that can then we won't have those errors where we essentially have out of memory errors when we actually have enough available memory. Finally, that leads us to the last concept, which is garbage collection. And so typically, like if you have pointers in C++, you have this, or even Pascal, you can get this what's called the dangling pointer problem, right? It's where what happens is you have, for example, in C++, we can free a pointer that we've previously allocated, and then you can still have that variable around, and if you try to access it and utilize methods on that pointer, what will happen is it throws a weird error because you're accessing memory that's already been deallocated, and it can cause a problem, right? So the dangling pointer problem. In Java, we get around that with what we call garbage collection, right? And furthermore, this is a known security error, which is called a memory leak. So if you have a dangling pointer, so a variable that still refers to an already deallocated part of memory, that still refers to that location in memory, and thus theoretically, you could inject code into that location in memory, and then they can execute it if they make a call on it. And that leads us to all sorts of bad problems. So that leads us to garbage collection, right? So since many errors are caused by the improper deallocation, right, which is like what we just saw there, the dangling pointer problem, and since the burden of the programmers have to worry about, right, you should. What we would like to do is instead have the language system handle all those problems for us, right? The language system provides us with the ability to allocate. Well, why don't we let it handle all the movement of stuff in the heap, as well as the deallocation at the correct time, and we don't have to worry about. That's great. So there's lots of different ways of doing this. So the garbage collector goes in and checks, are there any remaining links to this object in heap, right? If there isn't, then we remove it. And that's it. So how do we do that, though, becomes the hard part. And so there's three approaches: mark and sweep, copying, and reference counting. So the mark and sweep approach basically says, what we're going to do is we'll go and we're going to use all the current heap links in a two-stage process, right? First off, we go and find all current live ones, right? Mark them, and mark all. We go mark all the heap blocks linked to them, right? And then we're going to make a pass over the heap and return any unmarked blocks to the free pool. So this is great, right? Seems to go through, make sure everything is in there in memory. It's supposed to be there, and if it's not, then we just clean it up, right? So we don't move any blocks, and so both kinds of inclusion errors are tolerated. So, you know, it'll work, but it's not the best. Then we can also use copying collection. So you have the copying collector. It divides memory in half and uses only one half at a time. So when one half becomes full, we find the live heap links and copy the live blocks to the other half, and then you compact the rest down, right? So the beauty of this is as we fill up one side, we swap it over to the other side, and then that compacts everything down and gives us all the free open parts that we need. And it simultaneously gets rid of anything we don't need. Gets rid of the problem with fragmentation. On other part, though, it does not, since it moves the blocks, it can't have any type of inclusion errors. So that's a problem, right? Finally, we have reference counting. So what we do here is each block has a counter of heap links to it, right? So as you create new things and you make references and copy references, it updates the counter as a part of the block, right? So what ends up happening is when a heap link is copied, we increment. When a heap link is discarded, we decrement. And what ends up happening is the second the counter goes to 0, we could effectively garbage collect that block. That's not necessarily what happens, right? But as the garbage collector gets turned on, goes to the heap, it can clean up all that stuff as it needs to. The interesting thing is it doesn't have to worry about using heap, doesn't mess with current heap links, so it kind of avoids a significant number of those problems that we saw earlier. But there is a problem, right? It will miss, so one problem with reference counting is it misses cycles of the garbage, right? So if we have circle which points to a link, some object in the heap, right, which then links to another object in the heap, which links to another one, which then links back to the first one, right? If you have a circularly linked list, right, this is a problem, right? So it has, if everything has a link to it, so we can never effectively discard any of these items, and so that's a problem, right? We have to figure out some way to get around this so that we don't have to deal with it. So, because now once circle goes null, right, nothing's pointing to the linked items in the list, but we can't get rid of anything, right? Because even though we decremented the count over here on the initial item, it still is set to 1. Nothing ever goes to 0. So this is not good, right? And the other problem is effectively that there's performance issues, mainly with the overhead of updating references is actually quite high, because it's essentially you have to keep running a bunch of loops. Managing that information is difficult, and then you have to go run this loop across everything every single time trying to figure out what's going on. But it does have a natural advantage, which is that this whole concept is naturally incremental, and when you're doing the collection, right, there's no real big pause trying to walk through and find every link to this thing. So it does this. It has the beauty of it's efficient in that it keeps everything up to date over time, but without having to go through the entire list of memory every time we want to make an update. But at the same time, it has issues in managing correctly the reference counters, and is not very efficient when we're dealing with circularly linked structures in memory. Now, there's been all sorts of refinements, right? So you have generational collectors, which divide block into generations based on age, and then we can collect things. The goal is to get rid of, to collect on more, we'll say, younger generations more often, right? The things that have been more recently used. We have incremental collectors, right, which only collect a small amount of garbage at any one time. They don't have to worry about the uneven performance of typical mark and sweep and copying collectors. So there are several languages which we know require garbage collection, like Java and the way it works, because there's no way to explicitly deallocate with a destructor. ML needs it because of the fact that it can have functions defined within functions, and mixed with recursion and functions can return functions. Functions can be parameters. So ML has to have it, and other languages similar to it. Some languages like Ada and their implementations encourage it, but other languages make it actually extremely difficult to handle this because of their ability and their exposure of memory. So C, C++, right? You can do it, but and then I think managed C++ in that's the .NET version actually can handle some of this. And there are some libraries that replace the usual malloc free with the garbage collection manager, which is awesome because that makes it a more secure version of C, C++ than your typical version. It gets rid of certain dangling pointer problems and overflow errors. So, good stuff. And now it's and ever since, like, I would say essentially Java, when it became very popular, started making the idea of using garbage collection. Probably really started to popularize it. And it had a pretty good implementation. It's not the best. I mean, I mean, nothing is as good as explicit deallocation, right? And it does definitely save time and does not cause significant errors like with the dangling pointer problem, along with many others. So I would see the argument for developers wanting to use it. One, for runtime debugging issues are not going to become a major problem. Furthermore, it also gives us, assuming that it's been implemented correctly, improved security of your code. But it does have performance issues that we have to be aware of. Finally, the overall goal of this entire lecture is just that you understand that the management of memory is extremely important in all these language systems, in any language system that you're dealing with, whether you have to do the allocation yourself, straight up, the allocation and deallocation yourself, or whether you're using a garbage collection system. Know that regardless, everything has to have this underlying, all language systems have to have an underlying memory management system itself. So there are many different techniques, understanding how they basically work, as well as what are the possibilities for them and what are the problems associated with them, is definitely an active area or an active thing that you need to be aware of in the languages that you choose, but also understanding that this is one of the research areas and experimentation areas in language system research. Furthermore, this has implications on if you were to develop a compiler and a language system and what you may or may not have to do in order to actually make this stuff work when you start considering the development of an object-oriented system or any system that has a large number of types, and where would you allocate them and how would you allocate them. Anyway, I think that's about it. I know this is probably a long video, 47 minutes, but it shouldn't be too bad. Have a good day, and I'll see you all in class.